Hi everyone, I just wanted to take a few minutes here and provide a brief lecture to go along with this PowerPoint. Just to make you aware, this lecture in the PowerPoint is intended to supplement your reading. It's just going to cover some of the basic and really big ideas out of the chapter. So it's really important that you continue to read all of the information presented in Chapter 3 to get a good understanding of everything that we're trying to get out of the chapter. So with that said, we're going to take a look at Chapter 3, which covers minerals and rocks. Now to start getting an idea of how rocks form, we're going to start way back at the beginning and take a look at atoms and look at how they build up to eventually form rocks. So in order to begin understanding of rock formation, we have to do a brief review of some basic chemistry. The matter that makes up the rocks we see is composed of various combinations of basic elements that are made up of atoms. So this is basically what is going to eventually lead to rocks. If you look at this flow chart, we have atoms combined to form elements, elements combined to form minerals, and those minerals then combine to form rocks. So we're going to start at the beginning with atoms. Atoms are the smallest part of a chemical element. They are made up of three basic structures: protons, neutrons, and electrons. Some important things to remember about atomic structure is the number of protons determines which element an atom is part of. They typically have the same number of protons and electrons, so that atoms in general stay neutrally charged or have a charge of 0. And if you look at the periodic table of elements, which is where all elements are listed, you'll see they have an atomic number. And what that atomic number refers to is the number of protons that are contained within that element. So here's the basic structure of an atom. As you can see, we have protons in the middle here, indicated by the plus charge. The red circles are your neutrons, and out here, orbiting those protons and neutrons, which are contained in the nucleus, out here we have the electrons, which are contained within these orbitals, and they're constantly in motion, orbiting the nucleus. Now, one really important thing to understand about atomic structure is that in order for an atom to be considered stable, they try to get these orbitals full. So for an orbital to be full, the first one will have 2 electrons, and then a stable atomic structure will have 8 electrons orbiting in all the orbitals outside of that. So in these orbitals, the stable arrangement is going to have 8 electrons on the outermost shell. So that's a really important concept regarding atomic structures, those 8 outside electrons. So what happens then is these atoms combine to form chemical bonds. So understanding the structure of an atom is important because it determines how elements bond together. There's 4 types of chemical bonding that we're going to talk about. They're ionic, covalent, van der Waals, and metallic bonding. And again, just to point out again, the key to understanding bonding is that the electrons orbiting the nucleus arrange themselves into orbitals. These orbitals are considered stable if they have 8 electrons in their outer orbital. Bonding occurs because elements are trying to reach this configuration. So our first one is going to be ionic bonding. The definition of an ionic bond is electrons between elements are attracted to each other. So atoms donate or accept electrons in order to reach the stable arrangement of 8 electrons in the outer layer. So in this illustration, you can see here, this is sodium and chlorine. So they bond together to form sodium chloride, which is just your typical table salt. And if you take a close look at the way the structure is illustrated here, We have sodium, which has 11 protons in the nucleus, so that means it has 11 electrons orbiting it. And if you take a close look here, the first orbital has 2, and then we have 8, so there's a total of 10, and then we have the next orbital only has 1 electron hanging out here. So if you remember, we're trying to get to 8. So if you look at the chlorine then, we have 17 protons, which means there's 17 electrons orbiting that nucleus. So you have 2 here, 8 here for a total of 10, and then the outer only has 7. So what both of these elements are trying to do is get to 8 in their outer shell. So what happens is this electron right here moves over and donates it to this chlorine. So now this orbital is going to have 8, and you're going to be left with only this orbital, which is going to have 8. So that becomes a stable configuration because both elements have 8 in their outer shell. Now, the important thing to understand is that this doesn't just happen once and it's done. These electrons are continually in motion, swapping electrons back and forth in order for this bonding to be maintained. But the key thing to remember and understand is that there's a donating of electrons from one and an accepting of electrons from another, which is what creates that bond. They stay attracted to each other. The next one is covalent bonding, where instead of actually giving one to the other, in order to reach the stable configuration, the electrons are shared between both types of elements. So in this case, we have a carbon that is bonding to 4 hydrogens. So hydrogen only has 1 electron orbiting its outer shell, and carbon, which has an atomic number of 4, has 4 electrons represented by the X's. So in order for carbon to get 8 in its outer shell, it needs 1 electron from each hydrogen, and then for hydrogen to become stable, it only has that first orbital, which only needs 2. So each hydrogen shares 1 electron with carbon, and the carbon shares 1 electron with each hydrogen, resulting in a total of 8 for the carbon and 2 for each hydrogen, which results in that stable arrangement. The next one is van der Waals bonds. This is weak bonds, weak attractions between sheets of ions that themselves are likely to be bonded by either covalent or ionic bonds. So if you look in this illustration here, you can see you have positive and negative here, and negative attracted to this positive, and they all kind of line themselves up in these arrangements to create these slight bonds of attraction between each element. And then finally we have metallic bonds. These form between metal elements, and this is where sharing occurs between all atoms, rather than specific atoms within the compound. So you basically have all the same elements, some sort of metal element, and they go through that sharing process in order to form those metals. So that's really an important concept to understand regarding how these minerals form is those concepts of bonding. It's just the sharing or donating of electrons, which holds all these different elements together. And what that leads to are the minerals that are eventually going to lead to rocks. So for something to be a mineral, it must meet these 4 conditions. They're naturally formed, they're solid, have a chemical formula, and have a crystalline structure. And we'll take a look at a crystalline structure here in a couple slides. So all of the bonding that was just discussed creates regular geometric arrangement of the atoms. This is known as the crystalline structure. Figure 3.7 in your book shows some really good examples of how different crystalline structures look for various elements, so make sure you take a minute to take a close look at that figure. That crystalline structure and that geometric shape is going to be one of the determining factors if you were to ever try and identify different elements. So those minerals then are going to form together under various circumstances to create the rocks that we see. So there are a number of different groups of minerals that form rocks. We have silicates, which is the biggest and most common one, carbonates, oxides, sulfides, and native elements. And table 3.2 in your text gives some really good examples of the chemical composition and the types of minerals that each of these groups contains. All right, so just to review then, we have atoms formed together that make elements. Those elements bond, those different types of elements bond together to make various minerals, and the minerals are what are going to lead us to rocks. So a rock is basically just an aggregate of one or more minerals. And rocks are formed by a process that is described by the rock cycle. Now, a couple things to understand about the rock cycle is it's a worldwide rock cycling system. So that means it takes place over large scales, over large areas of the Earth, and all those different internal Earth processes that we discussed last week are going to take place. And the other big thing is that it connects the subsurface activity that's going on to the surface process to form the rocks that we actually see. Now this diagram, which describes the rock cycle, is really one of the big key things that you want to focus on this week. This does a good job of summing up all these different processes and how they're connected to each other. So as you can see here, we have igneous rocks, metamorphic rocks, and sedimentary rocks. And you'll read a lot more detail about each of those types of rocks in the book. But I just want to take a minute here to go over the details of these processes. So a couple things to note here. This is a simplified cross-section, looking down into the lower layers of the Earth structure, and notice that we have high temperature at the bottom and low temperature at top. So if we start down here with the bottom, we have igneous rocks, which is basically made out of magma, which is melted. So you can see, as described here, that part, the rock down here starts to melt. And then if it undergoes, if it experiences heat and pressure, it causes deformation, which is going to cause it to cool, move up in the Earth's layers a little more, and it will become metamorphic. It can undergo some more heat and pressure, and it could go through the processes of weathering and sedimentation, and if that moves up to the surface, it's going to deposit layers, and they will become sedimentary rocks. And if you take a close look at this, the reason these arrows are going both directions is it's describing the processes of how each type of rock can lead to the other. So that's really a big, key, important aspect of this chapter, is understanding this type of process. And the other thing you really want to pay attention to and think about as you're studying this rock cycle is how it relates to the plate tectonic activity that we discussed last week. So up here where we have the Earth's surface indicated, what you want to think about is how all the surface that exists on those plates that are moving because of plate tectonic activity is creating various scenarios for rock to move up to the surface or break through, and how those processes might cause melting down here. So it's this big connected process that leads to these three types of rocks, and that's really the big thing that I want you to try and get a handle on out of this chapter, is how these rocks form and how it's related to plate tectonic activity. So with that said, there's a few more slides. You can go ahead and read through them. And again, make sure you are continuing to read